We have been discussing the typed lambda calculus. So just for a quick recap, we are calculus expressions, the syntax of it, and then we have in module 3 we have talked about lambda calculus semantics, which is the reduction processes to get it to a normal form and all its consequences. And now we are typifying the lambda expressions. So we started with a simply typed lambda calculus expressions, which has the same builders as the lambda expressions we started with. So I hope the presentation is visible and I'm audible, right?
Yes, sir.
Okay. So
Yes, sir.
So we have, just for a quick recap, we have assumed a arbitrary collection of constant types TC, and then the type expressions could be any such constant type, which is known a priori, or a function type, or a parenthesizing of the types. So based on that, we said that lambda expression will be treated as a pre-expression when it is syntactically correct, but we still do not know if it is typeable. If it is typeable, I can have a type checker can deduce the type of that pre-expression. Then we say that it is an expression. And based on that, I am on slide 8. We have defined the pre-expressions of typed lambda calculus, which are the same builders as the type expressions, as the lambda expressions we have seen earlier. It could be either a constant from the type constants, a constant which belong to one of the type constants, or it could be a variable for which we are assuming a collection of expression identifiers EI, and or it could be an abstraction where the parameter has a type, or it could be an application, and we have parenthesizing for convenience. And based on those, we have now in slide 12, we tried to build the free identifiers of an expression through a recursive definition, which similar of which we had seen in the semantics also, so that we get to know the free expressions of an expression, free identifiers of an expression. Anything which is bound by a lambda binder is bound identifier. So they are like the parameters and local variables of a C function. And anything which is not bound, like a global variable in a C function, are free identifiers. So on slide 13, we talked about having a static type environment, an environment which associates type with free expression identifiers, so that I can actually talk about the type of the whole expression based on the type of the free identifiers as associated in the static type environment. So if we change those associations in the static type environment E, then necessarily we may have a different type for the expression. And based on this, we talked about having a set of type checking rules. I'm on slide 15, a rule for identifier, where we given a type of an identifier, we add it to the environment, or type of a constant, which is known a priori, and given the type of the parameter and the type of the function body, I can have the type of the lambda abstraction, which defines the function. And similarly, given the type of a function and the type of the argument on which the function applies, I can have the type of the application, and parenthesis does not change type. So using these rules, I'm skipping over to slide 22, where we first worked out an example, and we in slide 28, we showed the ladder diagram, which is typically used to deduce apply type checking and deduce the type of a lambda expression. Right? And there were several examples and practice problems given. I hope you have tried some of them at least, so that you can have a good idea about the type association. Now what we'll do is, well, it is true that lambda expressions as given can actually express the semantics of any programming language construct, but it is not very convenient to write that, because in programming languages we are used to certain type builders which are very, very common. So what we will do is to get the lambda expressions and their types closer to the programming languages that we typically see, we will extend this lambda calculus with different kinds of extended types. And on slide 43, we summarize that we will extend the simply typed lambda calculus, which is written with a capital lambda with an arrow on top, to a extended type lambda calculus, which is written by this notation of capital lambda an arrow, but it's a subscript of double r. And typically these are the types that builders that we will use. The builders are tuples, making a collection of values, builders of records which have named component identities, a sum type which is very, very interesting, and it is not it is something which kind of represents, you can say, the union that you have in C, but in a lot more formal way. We will have to understand that semantics and the type of reference. We will talk a little bit about array types also. So this is the point where we start the discussion today. So a tuple is an ordered sequence. It is written in this form. Say a tuple of n number of values a1 to an is written in an ordered form. So this ordering is important. It's not like a set. So a1 has to be followed by a2, finally up to an. And we use angle brackets to designate that it is a tuple. So it has a type which is T1 cross T2 cross Tn, where A1 has type T1, A2 has type T2, and An has type Tn, which is very understandable. So if I have a, say, if I'm representing a complex type, we say that it has two components, say real and imaginary, and each component is of double type. So what is the type of the complex? It is double cross double. That is, any pair of double values would represent a complex number. So it's very similar to that concept. So we are having an ordered type. And I have already mentioned that the reason that we significantly use tuple type is for representing functions which take several parameters. So if it takes several parameters, then we can bundle these parameters as a ordered tuple and make it a single parameter, and thereby restrict all our rules and descriptions and discussions to functions of one variable only, which will become this ordered tuple. Okay. I'm sorry. So in terms of tuple type, we introduce an operation which of projection. It is written as proj I, where I is an index value in this ordered tuple. So I can be from 1 to n. So what it does, given a tuple, it actually extracts the ith component of the tuple. So if I have a tuple a1 to an, proj I on this tuple will take out ai. So I can have proj 1, proj 2, up to proj n to take out every individual component of the tuple. It's a very simple concept. So if we actually think of a function taking the tuple type, so it has an argument. Look at the second line of the lambda expression here. It has an argument which is of the type of product of T1 through Tn. And then when we want to apply, when we want to define the body, in the body, we will use some ith component of this tuple. So this is proj I of the argument, which will give me the ith component, and let's call it IDI, and we will be able to use that. Now, for this, we use a shorthand notation, which is given on the top. That is, I will say ID1 colon T1, ID2 colon T2, IDN colon TN, which is a lot more familiar with us, which is a typical way we write, say, C functions. So let us take an example. We have lambda x colon integer, lambda y colon integer. So there are two parameters here, x and y, and we will say plus xy. Now, if I write it in tuple notation, which is actually mathematically what we mean, then we have a tuple P of type integer cross integer. It's a pair of integer. And then plus applies to x. What is x? X is the first component. So plus first argument of plus here would be proj1 P. That is projection of the first component of P. Second one, which is y, is projection of the second component of P. So this is that simple way to represent that. So that is about the tuple type. Let me just check back if there are any questions. Any questions, friends? No, it is pretty straightforward. Okay, good. So let us get back and continue. So this is the first type in the extended lambda calculus is tuple type, which we have just introduced for NRE functions. Now the second extended type that we introduce is record, which is like struct in C or class in C++ and so on. So what is the difference of record from a tuple? It also is a collection of multiple values having multiple different individual types. But in terms of record, the components are not, it is not important in terms of their order. But what is important is every component has a label, has a name. So typically when I write the complex type in C, I use a struct and say RE, double IM. So RE is the label of the intended real component of type double. Component IM, the data member IM, is a label for the imaginary component intended having type double. So here you can see the way to write the record. So there are n labels, L1 to L2 to Ln. Each has a type T1 and the corresponding expression M1, which has to be of type T1. So we record of this form, the type is written in the form. Of course, this is a record which has values. So it is like saying that if C is a variable of complex type, then C dot RE, say, is 2.5, which is M1. C dot IM is, say, 3.6, which is M2. So that is the way you write the record. And the type of that record is label 1 having type T1, label 2 having type T2. In this way, label N having type Tn. And to extract every component from the record, we make use of the well-known dot component, dot notation or dot operation with the label name. So if we are given a record, then dot li will take out the expression corresponding to the ith label li. So that's the, you can see the parallel with our well-known C, C++ or Java function, Java languages. So record is, I think it's too simple to miss anything. Now we come to something which is very, very interesting. It is a sum type. You can think of it as a union, right? So what is the difference if you think of C? and that is the closest that you can get. What is the difference between a struct and a union? We say that both are collections of multiple fields having different types. But in terms of struct, all components are present in a value. But in terms of union, any one of the components can be present, not all of them. Any one of them, any one of the n components can be present. So that's why it is called a union. And typically in C, the responsibility of remembering which component a particular instance of union is carrying, that responsibility lies with the programmer. But here we will have a mathematical notion into that, mathematical operations into that. So we say that T1 plus T2 plus Tn represents a disjoint union of types, where each element contains information to indicate which summand it came from. That is, which of the type it comes from, even when several of the types could be identical. It is not necessary that they are distinct, but it is a disjoint union. That is, any instance of this type will be an element which is of any of these n types. Right? So if M is an expression of type Ti, then we create a sum type expression by this operation. Just look at it very carefully. The operator is called in, standing from inject. So as if there is a domain of n types and you are injecting a particular value into this union. You are setting a particular value. For which component are you doing that? You are doing that for the ith component. So for the ith component, if you inject the value, then the value that you inject or the expression that you inject must be of type Ti. So if M is of type Ti, then you write in subscript I, meaning the ith component. You write T1, T2 up to Tn to list the types that make this sum type. And within parentheses, you write the expression. So that injects the value M into the ith component of the sum, T1 plus T2 plus Tn. Now, how do you take out a value? So how do you extract a value? This is how you are creating a sum type value. So if I have a sum type expression M, naturally having type T1 plus T2 plus Tn, then we write a case expression. So we say that case M of, what is M? M is an expression of type T1 plus T2 plus Tn of some type. And then we write n different parts into the case. So we say that case M of x1 colon T1. That is, if this sum type expression has been created by injecting an expression in the first component, which is of type T1, then we take that component expression is x1 and its value is E1. So x1 is what goes into E1. Similarly, you'll have x2 colon T2, then E2, and in this way, xn colon Tn, then En. So it represents a statement listing the possible expressions to evaluate depending on which summand of M is a power of, right? So, I mean, it is the actual implementation we'll think of in a little later, but conceptually, if you have injected the ith component to create the expression M of the sum type T1 plus T2 plus Tn, then when you do case M of, you will get xi, the ith component that you had injected, and that is using that xi, you will evaluate the expression ei, which can actually vary. Thus, if M was created by this injection for some M primed of type Ti, then evaluating the case statement will result in evaluating Ai using M primed as the value of Xi. This is what it means. Yeah, I mean, I know it's sounding little complex, but we take example to understand. Okay, so let's start with an example which is the simplest that you can have. You have only two types, and let us assume that both of them types are integer. So T1 is integer, T2 is also integer. So I can create an expression M1 of this sum type integer plus integer by injecting this constant 5. You know those constants. That's the reason as constants in lambda calculus. So it is written by 5 underscore. So I inject this expression, which is of type integer, expression 5, as a first component in 1. And I'm listing the types here. So this gives me a expression of some type where the first component has been set as 5. Similarly, going below, I have another expression M2 of the sum type where 7, constant 7 has been injected as the second component. So this is now another sum type expression. Right? So we have created these two, M1 and M2. And now let us try to evaluate an expression. So I am defining an expression, say my case, which is lambda z colon integer plus integer. So the binder is on z, which is of the sum type. Then the case expression is case z of, because you are trying to, you would take a sum type value, which is z. Then you say x colon integer. That is the first component type. If z has been created by injecting in the first component, then I say, let us call that value as that expression as x. So it is of type integer, and we evaluate the E1 is x plus 1. So we are creating successor of that. Or if z has been created by injecting the second component, then you take it as y, again of type integer, and you do y times 2. Right? So what will happen if I apply my case on M1? Let us go back one slide to 49. M1 was created by injecting 5 in the first component. M2 was created by injecting 7 in the second component. So if I apply M case M1, then Z is M1, which has the first component. So that becomes X. So X is now becoming constant 5, which we had injected. So E1 is evaluated with the value of X as 5. You get 5 plus 1, 6. But if you do my case on M2, so Z is M2, which is injection of 7 in the second component. So Y now becomes 7. It is an integer. And E2, the second expression, is evaluated by taking Y as 7, 7 times 2, which gives you 14. So this is how you can mix any set of types and use them. Okay, let us take a little bit of a more advanced example. I'm taking a sum of two types, one of which is an integer, and the second is a function. So it is a sum of integer and a function from integer to integer. So in M1, I inject 47 in the first component. So what is 47? 47 is going in the first component. So 47 must have a type integer, which it does. It's a constant of integer. Right? So M1 is a sum type expression where the first component has been injected the number 47. Now let us create another sum type expression M2, and in this I inject in the second component. If I inject in the second component, then the value that I inject, expression that I inject, has to be from integer to integer, a function. So I inject the successor function. So I kept that successor function. What does successor function do? It takes a number and finds out, adds 1 to it, find out the successor. So it takes an integer, gives you an integer. So successor is of the type T2, integer to integer. So injecting it in the second component will give you M2, which is again an expression of this sum type. Right? So this is this. So we have created two different expressions of the sum type integer plus integer to integer. Right? So now let us try to use it in evaluating an expression. Say I have a lambda binder on y, which is a value of the sum type. I say case y of the sum type. And if I have the first component, which is here x1, I call it x. It has to be of type integer because this is integer plus this. So if that is if it has a first component, then I take that component x and compute x plus 1. Right? This is my expression that I evaluate. But if y is injected, created by injecting a second component, which is integer to integer, then I call it f. x2, I call it f. It has to be of type integer to integer because it's a second component, t2. And in that case, my expression that I evaluate is f0. That is, I take this function f and apply it on 0. So if I do this for the M1 and M2 that we have created, M1 was created by injecting 47 in the first component. So if I do is first on M1, y is M1, it has the first component, so that is x, which is 47. I do x plus 1, which is 48. If I do is first M2, which was created by injecting the successor function in the sum type, then y has a second component. So f becomes the successor function. So the value that I evaluate is successor 0, which is 1. Right? So that is how we can use any kind of mixed type to actually create a sum type expression. So what I stated is written at length in this slide 53 for your subsequent understanding. Right. So let me stop here and see if there is any question. Because this is the sum type where tuple and recorder types, type builders that you have seen before. Sum type, though it parallels union, you have certainly never thought about it in that manner. You have always taken union as a loose kind of struct where the whole focus that is given in C is said that, well, this is done to minimize the memory storage because it can store any one value at any point of time. But the most important fact of union is it can give you an aggregation of multiple types, a disjoint union of multiple types. And we are, by the sum type, we are actually trying to represent that in our lambda expressions. So is it clear? Do you have any questions on this, friends? No. Okay. So let us go ahead and look at some more examples. So I'm creating a sum type now using 3 types, a sum type of 3 types. One is integer, another is integer to integer, a function type, and another is integer cross integer, that is a tuple type. Right? So I have a simple type constant, I have a simply built function type, I have a tuple type, I have a sum of these three as union, and I have created three expressions based on this sum type. So M1 is where I inject the first component. So I have to inject an integer value because it has the type integer. So I inject 25, let's say. In the second expression of the sum type M2, I inject the second component, which has to be from integer to integer. As an example, I'm injecting the successor function as I did in the last example. As a third component, I inject a tuple because it has to be a doublet of integers. So I inject a tuple 1221 in this. Right? This is the tuple notation. So these are the three expressions, M1, M2, and M3 that I have created. And I have one case expression for evaluation. So again, the same notation, y is lambda is bound on y, and it is of type, the sum type, the three types disjoint union together. Case y of, so given a sum type value expression y, if it is injected in the first component, I call it x. It has to be of type integer, and my evaluation would be plus x1. That is what I'm defining. You can have any consistent expression here. If y has been created by injecting the second component, then I call it f. It has to be a function from integer to integer. And this is what the expression that I evaluate. I apply f on 7. I mean, just arbitrary choice. If y has been created by injecting the third component, which is a tuple, I call it t. It has to be of the tuple type integer cross integer. And then I do this expression, which is basically adding the two components of the tuple plus proj1t, because that will give me the first component of the tuple, and proj2t, which will give me the second component of the tuple. Right? So this is what I have created. So what will be the values? Is first M1. M1 is injected the first component. So if y is M1, then I'll have the first component. So x is 25. I will do plus 25, 1. So I get 26. If I do is first on M2, if I apply is first on M2, M2 has been injected with the second component being successor, being suck. Y is M2. It has the second component. So f is the successor function. And then I apply the successor function, which is f, onto 7. So I'll get the successor of 7, which is 8. If I apply is first on M3, M3 has been created by injecting a tuple. So y is M3. The third component has been injected. So that third component is t of the tuple type integer cross integer. I do plus of the first component of that tuple, proj1t. So that will give me 12. And then I do proj2 on t, which will give me 21. So I do plus of 12, 21, which gives me 33. Right? So this is how you can, you can just keep on extending. You can have more and more and more types in the sum type created. Right. So now I take another example where one of the component types is itself a sum type. So I do a sum type of integer and sum type of integer plus integer. Right? So I do a disjoint union of integer and the disjoint union of integer with integer. Right? So I create three expressions. In the first component, I inject 10, which is simple. Now, for the second, actually what I'll have possible injection in, since the second part is a sum type, so I actually have two types there, the second and the third. So I'm representing as second or third. So if I inject in second, then I'm actually injecting in the first part of the sum type that I have taken here. So for injecting in second, I have to actually inject here in terms of the first component. So I inject in the sum type of integer and integer, the first component 12. Whereas in the next one, I inject in the second component of this sum type, which is 14. Right? Then I have a example case expression where y is of type integer plus integer, which is the sum type itself. So if it is a first component, then y is an integer. I call it, y has been injected with an integer in the first component. I call it x. I take that integer, add 1 to it, plus x1. If it is a second component, then it is a sum type itself. If it is a sum type itself, then again I will need another case statement to take out the types and evaluate it. So if y has been created by injecting in the second component, I call that second component S, which is a sum type. And then I define another case statement where the case is on Z, which is a sum type. And if Z has been created by injecting in the first component, I call it A. I add 2 to it. If Z has been created by injecting in the second component, I call it B. I add 3 to it. Okay. So now if I evaluate using M1, M2, M3 is first applied on M1, I have the first component. So X becomes 10, which was injected in the first component. I add 1 to it, I get 11. If I apply it on M2, then I get the second component. S is the second component that I have injected, which is this whole thing in one integer, comma integer 12. So it is a sum type where I have an injection in the first component. So Z is this in one integer, comma integer 12. So it has an injection in the first component. So that becomes A. So A becomes 12. And I do plus 12, 2, I get 14. Similarly, if I do it for M3, I have injected in the second component. So I again get S. And in S, I have injected in the second component. So Z is into integer, comma integer 14. So Z has a second component injected, which is B, which becomes 14. I do plus 14, 3, which is 17. So this shows that how I can keep on, mixing up any types and taking union of them. So let me stop and check if you have any questions.
Sir, in the expression of M3, shouldn't it be in 2 instead of in 3?
Exactly. You are right. It should be in 2. It should be in 2. Right. That is a typo. I'll correct that, because you are injecting in the second component of the sum type, and in that the second component itself is a sum type. So you are again injecting into the second component. You are very right. That's a typo. Okay, great.
Yeah. Okay.
So
Thank you, sir.
great. So this clearly tells me that you have understood. So friends, this is what I mean. I'm very sorry about this typo. So this should be in 2, because you're injecting this whole thing, which is an expression of the sum type integer plus integer, as a second component in this type. So this should be into. I will correct that before I again circulate the presentation. Okay. Thank you for pointing out. I did not ask the name, wherever it was. Okay. So this is the sum type. Now there are a few things that come as a corollary in using the sum type and the case expression. If you have noticed here, or let us go back to the let me go back to the first example, and let me highlight 2 points. What is, if you have seen here, these 2 component types were integer, and the result of the expression was integer. Right? We have just done simple operations on that. In the second example, again, one was an integer, another was a function from integer to integer. But if you look at the result of this case expression, this was x plus 1, which is an integer, and this was the function integer to integer applying on an integer, giving me an integer. So the result of the case is an integer. Let's go to the third. This is what we did. For an integer, we added 1. For a function integer to integer, we applied it on an integer to get an integer. For a tuple type, we added these components. We could have done something else also, but the result is always an integer. The point that I'm trying to make is a case expression will always have expressions e1, e2, e3, en. All of them must have the same type. For example, if I said that, well, if this is integer cross integer, then I say plus proj1. I do not write the proj2. What happens if I write plus proj1? Then I'm done a carrying. So plus proj1 will take an integer and give me an integer, right? So the type of the third expression will become integer to integer, whereas the type of the other expressions are integer. Since you do not know in a case as to which component may have been injected, if you have different resulting type from a case expression, then you get a inconsistent semantics, right? So whenever the case expression is written, E1, E2, if I go back to the original definition of the case expression, this is on slide 48. You can see there are n expressions given that you are summing n types. These types are all different. T1, T2, Tn could be anything, but the result of evaluating this expression must always give me the same type. Otherwise, that case statement is not, it has an undefined behavior. So such case statements will not be considered. They will not pass through the type checker. So this point has to be, this point is not, this point is very critical to write a case statement and to do the semantics for that, that unless E1 through En have the same type, this whole case expression cannot have a type. So it is a built-in type error. The second point that you would like to note is the fact that, well, how do you really represent this injection? Think about the union type in C. So if you have used the union type in C, you will often find that a typical way to use that is if you just use a union type variable, then you do not know at the execution point as to which component of this union has been set. So the typical use model for union type is to wrap it in a struct where one component is a tag, typically an integer or an enum, and the other component is actual union. So what you do in the tag is, in the tag, you write down the, say, the order number, the ordinal number of the component of the union where you have actually put the value. So if it has, say, 2 values, one is int, one is double, the first one is int, the second one is double, then when you have put the value int, you will put the tag as 1. When you put the value double, you'll put the tag as 2. So while you use it in the program, you will not have to remember. All that you do is take that struct variable, take the tag component. If it is 1, then you treat the union as an integer value. If it is 2, you treat the treat the union as a double value. So this is a typical programming trick you do, and that's exactly what the injection is doing. So what injection does, it puts that value and puts a tag, giving the fact that it is the ith component having the TI type. Right? So this is the basic notion of the injection. One injection is basically creating the value with a tag, which tells you which component it is. And once you think of it in that way, I'm not saying that this is necessarily the way it is implemented. The implementation could have different ramifications, but this is the way you find it convenient to think of, that it has a tag. So M has a tag inside which tells it which component has been set, and you jump to that part of the case statement, and then you know what is the type of the value, that expression that you are going to extract and call as xi, and apply it on ei, which, as we have discussed, will have to necessarily give you a unique result type, which is not shown in the case statement. And we'll see as we do type inferencing, we'll have to get to that type of the case statement, which is the type of E1 through En. Right? So these are the 2 points, that is uniformity of the result type and the basic notion of having an internal tag to represent injection, are the 2 insights that you must carry in terms of the sum type. This was the more difficult, extended type that we deal with besides tuple and record. The third is very well-known reference type. So if an expression has type ref t, then you are talking about denoting the location which holds the value type. So far we have not talked about location, so we are bringing in location. So we are trying to slowly get closer to the programming language, because so far we have not talked about memory at all. So there's no location, but now we are trying to represent locations. We say that M is of type ref t, which means that it is a location which can hold a value of type t. And then we can have an expression val m, which is basically taking out the value that is there in that location. So dereferencing, simple dereferencing that you are talking of here. Now this has this is something which is very explicit in lambda calculus, extended type lambda calculus. In a standard programming language, usually do not do this difference between the value and the address, the location. For example, if you see in C++, we say x assigned y. X looks like x, y looks like y. But depending on the context, y occurs on the right-hand side of the assignment. We call it a R value, which means it is the value that it represents. If it is 3, it represents 3. Whereas x occurs on the left-hand side, we call it a L value. It actually represents the address of x, because y has to get assigned. So the value of x does not matter. It will get erased by the value of y. But what you need to know is the address of x. But we do not explicitly write that. In a normal, usual procedural language, we make it out from the context where the variable is occurring. But there are languages like, say, ML. ML is another functional programming language where if we write x, it means the location. The default meaning of a variable is a location. And if you want to find the value it stores, you need to write it as exclamation x. Right? So it makes a difference between the two. Even in C, if you want to have the location as an R value, here you get x assigned y, you get location as an L value. But if you need location as an R value, you can use ampersand x. Right? You know that. So all that semantics is now getting kind of represented at the lambda level through this mathematical representation of the reference type. In reference type, you have a special constant null, such that it means a null reference. That is, there is no reference there. So if you evaluate val null, if you try to find the value of the null reference, it will always be an error. Right? Just parallels your C notion of null pointer dereferencing. Right? So if M is a reference of type ref T, N has type T, then the expression N assigned to M denotes an assignment. So this is the typical, you know, more like procedural representation which we are now bringing into the lambda calculus. But type wise, we have to say that this assignment is type correct if N has a type T and M has a type ref T. Right? So this is the basic reference type that we are. Now, finally, certainly you will you would like to know about the array type, because that's a common builder. We have done kind of in tuple. We have done just collections, ordered collections, which is what you do not have a fixed builder, but you use often in function calls. We have done record type, which parallels struct. We have done sum type, which parallels union. We have done reference type, which parallels pointer and reference, something in between. And certainly the most common builder is array type, where you have values of a certain type, a collection of values of a certain type, put as an ordered sequence where the index can get you the value. So A3 is this. So A0 is 5, A1 is 3, A2 is 8, and so on. Now we will say that, well, this we can represent in lambda calculus by a function. I say this an index function. A index takes int I, which is the index, and then it does a switch of 0, 1, 2, which is a in index values, and returns this corresponding value. So if you replace AI by index I, you will get the same computation. So array is nothing but a function, right? So we will be able to use arrays by just using our function model. Well, that's very good as long as you are accessing an array. Now, what happens when you want to make an assignment to an array element? Say A1 is assigned 4. So if you do that, then you had the index function as 051328. Go back. 051328. Right? This is the index function that you had. Now, if you make this assignment 4 to A1, then you have an index function which is 051428. So assignment to an array element means that you take one index function and you return another index function. So if I model the assignment as A assign, then actually I take my original index function, I take the index to the item, which is 1, I take the value to set there, which is 4, and I get a new index function. So you can say that assignment to array components are higher order functions, right? Because they take functions and have to return functions. So they can be handled by the type of higher order functions. But not only that, so we know all of that, higher order functions and all of that. So kind of that helps us get to the array type. But there is some more to that, because you cannot just work with integer, because arrays do not have infinite number of indices. It has a finite range of indices. So you need a subrange of integer for the index type. So we need to define a subrange type to be able to actually define the array, because this is this index function is actually not on the int type, which I have written here, because it will have error for any value which is outside of 0, 1, 2. But it is kind of an enum or subrange type of 0 to 2 on which it has to work. So that also needs to be modeled. We will do that more, because arrays can also be kind of thought of as contiguous memory locations, and we will try to see how we model this as we go forward. But initially now we will restrict ourselves more to the tuple, record, sum, and reference type. So with that, we will build the type expressions. But today we are completely at the end of time. So let me know if you have any final questions. Otherwise, we'll stop here. Any questions, friends? So we have just introduced extended type lambda calculus with four type extensions of tuple, record, sum, and reference, with which we will bring the type lambda calculus expression very close to our normal usual programming languages. Any questions? No. Yeah, okay. We are completely out of time. So thank you very much for your attention. We will meet again on Wednesday with our class quiz, and the timing of that, the access of that, all of that will be let known to you through mail. And in the slot of 8 to 10 on Wednesday morning, we will hold the quiz online on Moodle, and you will be tuned to get information on that. And syllabus, as you know, is up to module 3. That is, type lambda calculus is not included in the syllabus of the quiz. Have a nice day, and bye.